Hi, I'm Brian Carlisle, and this is the West Coast Division of Unimation. We're involved in the development of advanced robotics concepts. We see mobility as one of the key attributes of the robot of the future. The mobile robot should be able to move about without requiring drastic changes to its environment. Ideally, it should need no more room to maneuver than a person, nor should it need wires buried in the floor for guidance. The robot should be capable of autonomous navigation. The important thing to notice about this vehicle is that it is omnidirectional. It can move in any direction without having to turn first. This particular design was developed and patented by Bill Law, presently with the Veterans Administration Hospital in Palo Alto. The key to the design is the wheels. Mr. Law's wheel concept was refined and developed here at Unimation. As you can see, the wheel has a series of rollers around its perimeter. By a combination of rolling on the rollers and rotating about its major axis, the wheel can move in any direction. 3 of these wheels, each powered by an electric motor, are arranged in a triangle on the vehicle. An onboard computer calculates the necessary wheel velocities in order to move in various directions. The mobile base is controlled by the same controller as is used in our Puma series of robots. In fact, it is programmed using the same language, VAL. Those of you familiar with the Puma will recognize this manual control unit. The mobile base moves in a Cartesian coordinate system. Here, I'm moving in X and Y. The base can rotate about its own axis. It is possible to teach complex paths by teaching a series of positions in succession. One of the features of an omnidirectional vehicle is that it requires a minimum amount of room for maneuvering. Here, we are simulating a robot moving between workstations. A steered vehicle would have to back away several feet, turn, traverse, turn, and approach the bench. The omnidirectional vehicle simply moves laterally with a few inches of clearance. The vehicle presently determines its position by counting wheel revolutions. This is sufficient only for short distances on smooth surfaces. The major problem is in maintaining orientation. A small error in heading translates to a large error at the destination. One solution to the accuracy problem is to have an onboard navigation system which is capable of determining direction and has the ability to take sensor readings at periodic intervals in order to update its position. The vehicle should be able to sense its destination while it is some distance away and correct its path. It should mechanically attach itself to the dock in order to provide the accuracy and rigidity necessary for many robot applications. Shown here is some early work in dock sensing. Obviously, this machine is still a prototype and needs future development. 2 major areas are docking and navigation. We have several ideas in docking. The sensing system should be accurate to within 1/4 of an inch. We'll be exploring electrical and acoustical systems for this. In addition, the vehicle should have a mechanical latch which can pull it in to its final position and engage electrical connections. Finally, the dock should be both compact and portable. Ideas for navigation systems need to be explored. These include the use of gyroscopes for maintaining direction, acoustic sensing for obstacle avoidance and position updating, and various triangulation schemes using either radio or visual information. I've discussed some of our ideas for adding mobility to the robot. Of course, a great deal remains to be done. The focal point of our efforts will be to develop a vehicle capable of autonomous navigation. We see uses for this device in areas such as industry, as aids for the disabled, and perhaps ultimately as a household servant who, at last, will do windows.